In this video I will show you how to apply Lagrange's equation on a 2D system. So I'll be focusing on a two-dimensional system, and I will be using the Cartesian coordinates. So I will be using x and y. Okay, 2D. Now I have the kinetic energy. I know that this is 1/2 the mass times the speed squared, and really this will be 1/2 m. Remember, I am using Cartesian coordinates, so I have the square of the square root, that's what the speed is, vx squared plus vy squared. Now I will rewrite this in using different notation. Okay, the square root with the square will cancel out, and I will write vx as essentially x dot, because x dot represents, let me remind you, so x dot is dx over dt, and this is vx. And then I have the same thing for the y, so y dot squared. Now for the potential energy, the only thing that I will say here is that it depends on x and y. Okay, it does not depend on any velocity, it does not depend on time. I want to see what happens when I use this expression. The equation for the Lagrangian, ek minus ep, and at this point I'm just copying and pasting. Now here in the Lagrangian, I see that I have two generalized variables. One of them is the x and one of them is the y, and I need to write Lagrange's equation for both. So I will have the partial of the Lagrangian with respect to x is equal to d over dt, the partial of the Lagrangian with respect to x dot. Now, to actually move on from here, of course, I need to use the definition of the Lagrangian. But the first thing that I'm gonna do is say the partial of the Lagrangian with respect to x. So I'm looking here to see where I have x. Remember, a partial derivative means that I keep everything else constant. So the Lagrangian here, you can see, it depends on x, it depends on y, it depends on x dot, and it depends on y dot. Now, when I take the partial of the Lagrangian with respect to x, I am keeping everything else constant. So if you see here, I have 1/2 m x dot squared. The x dot for this partial derivative is assumed to be a constant. Y dot for this partial derivative is assumed to be a constant. The x, of course, that's what I'm differentiating with, and the y is a constant. So for this partial derivative, all of these go to 0, and the 1 of ep with respect to y also goes to 0. So then this will be the partial of ep with respect to x. And now here on the right side of Lagrange's equation for x, I'm going to start with the inner portion. I'm going to find first the partial of L with respect to x dot. And here, the only thing that it's changing is x dot, and everything else is assumed to be a constant. So for this partial derivative, I will have 1/2 m and then 2 times x dot. The 1 over 2 with the 2 goes away, so I have m times x dot. Now I'm gonna take this result, plug it into the left side, take this result, plug it into the right side. So let's see what that gives me. The left side of Lagrange's equation becomes minus the partial of ep with respect to x, and the right side is d over dt mx dot. But the mass is a constant, so this becomes mx double dot. Now, if I think about what this means, I know that the negative slope, the negative gradient of the potential energy with respect to x, this is simply the force in the x direction. So what I found is that the force is equal to mx double dot, or the force in the x direction is the mass times the acceleration in the x direction. This is a very familiar result. This is essentially Newton's second law in the x direction. That's what we have been using in introductory physics. Let's see what happens now in the y, with the y variable. So I have the partial of L with respect to y is equal to d over dt, the partial of L with respect to y dot. Now, before I move on, I will find what this is equal to, and I will find what this is equal to. So this is my Lagrangian. The partial of L with respect to y assumes that this is constant, that's constant, and x is constant. So this will be simply minus the partial of EP with respect to y. And similarly for the partial of L with respect to y dot, that's a constant, and all of these are constants. So what I have is 1/2 the mass times 2y dot, and this cancels out with that. I'm gonna use all of these three. This is the left side minus the partial of the potential energy with respect to y. And then I have d over dt, and the partial of L with respect to y dot is simply m times y dot. But because the mass is a constant, this becomes my double dot, and the left side, as before, is simply the force in the y direction. And again, this is our familiar Newton's second law in the y direction. So if you use Cartesian coordinates in 2 dimensions, and assuming that your kinetic energy is given by this expression and your potential energy just depends on x and y, you get the familiar equations for Newton's second law.